Welcome back to the lecture series on microeconomics, and we have been discussing linear programming problems. Last time we have stated the general standard forms of maximization and minimization type problems. We have discussed duality, and finally we had started discussing linear programming problems in the context of a production setup. So, let us now go back to the previous discussion and end that first, then we will continue with a numerical exercise to understand how these linear programming problems could be solved. So, note that we had this discussion earlier where we said that the optimized value from the maximization problem and the minimization problem shall be equal. So, what does that mean? So, that has a very strong implication in terms of economics. So, basically one can say that the economist while solving a dual problem shall try to find these imputed input prices or accounting values of these resources, which are basically find VIs such that the net profit of the firm becomes 0. So, what does that mean? That basically says that suppose you have a firm where some variables, some inputs are variable and some inputs are fixed, like capacity of a firm, warehouse space, machine hours, etc. So, there after computing all the variable costs, if you have per unit profit for a commodity, you now shall take care of your fixed costs, and the way to capture fixed costs is through these imputed prices for inputs which are given by V1 to Vm, and you should set them as high as possible so that your economic profit becomes 0. So, now we are going to continue our discussion on this production problem through a simple numerical exercise, because it is quite difficult to understand how to solve a linear programming problem using this m cross n production data setup. But before we go to solve a numerical problem, let me spend couple of minutes to discuss the process how LPP should be solved in general m cross n setup. So, basically the linear programming problems involve inequalities, but it is difficult to deal with inequalities. So, first we have to convert these inequalities into equalities. Let us see how one could do this. Okay. So, here let us go back to our previous problem, which is a general problem of profit maximization, the primal one. Okay. Okay, we are saving time by not writing the objective function. I hope we all know what was there. So, just let me write it was a profit maximization problem. Okay. So, now we will focus on the constraint number 1 in that case, because the method that we are going to discuss is general enough. So, what is valid for constraint number 1 is also valid for constraint number m. Okay. So, let us now look at the constraint. So, we had A11 times Q1 plus A1n times Qn, right, and that is basically less than equal to Xm, right. So, how did we interpret that previously? So, this is basically absorption of fixed input 1 in production of n goods, right. So, you can say that this is the demand side of the story. So, this is basically the input demand, right. Now, let us look at the right hand side here. What is this? So, this basically talks about the fixed supply of input 1, right. Now, as there is inequality of less than type, then basically there could be two possibilities that could arise, right. And what are these possibilities? So, of course, possibility number 1 would be that A11 Q1 plus A1n Qn is equal to Xn X1, and the other possibility which could arise is the following: A11 Q1 plus A1n Qn is less than X1. So, now note that in the first case, which is basically this, and this is the second possibility. Now, in possibility number 1, there is no problem, we get a linear constraint which actually we would love to get, right. Now, the problem emerges when we have the possibility 2 where we have strict inequality, right. So, basically we have to convert this strict inequality to an equality, so that it is easier for us to handle. How to get this done? So, of course, we can see that this right hand side of this inequality is basically higher compared to the left hand side of the inequality, right. So, basically there is a deficit, right. So, in terms of this production problem, we can say that there is some unused quantity of input 1. Okay. So, we can use a concept called slack variable, and the slack variable could be used to convert this inequality, strict inequality, into an equality. So, basically one can write or rewrite this expression as right. So, here this is one, this newly introduced variable is basically the slack variable. So, to convert m number of inequalities convert them, each of them, into equality, strict equality through slack variables, right. Now note that these slack variables which are given by capital S1, capital S2 for the second constraint, and then finally for the mth constraint Sm, these are also the decision variables, right, because we do not know their values a priori. So, by adopting this concept of slack variable, we get what is known as the augmented or slack surplus form of the linear programming problem. Okay. Now, let us move to the dual problem. So, dual was basically a kind of cost minimization problem, right. Okay. So, again we have linear objective function, but inequality constraints, we have to convert these inequalities into equalities. How? So, we are going to show that only for constraint number 1, okay, and what is valid for constraint number 1 is also valid for constraint number n as well. There are n number of constraints, remember. Okay. So, what is the first constraint that was there in the dual problem that we had seen earlier? So, A11 V1 plus AM1 VM greater than equal to the per unit profit from commodity 1. Okay. So, now again there could be two possibilities, one strict equality and the other one is strict greater than inequality. We are not going to write the same, but note that we can now introduce another variable concept which is known as surplus variable, and follow the same procedure to convert this inequality into equality, and this is the way we are going to do that. So, note that here we have a higher value in the left hand side. So, basically we need to deduct something from the left hand side such that it becomes equal to the right hand side, right. So, let me introduce this small s as my surplus variable that I introduce for my constraint 1, okay. And now if I take that extra part out, it shall equal to my per unit profit from commodity 1, right. Okay. So, here the small s1 is basically my surplus variable. So, similarly there will be some changes in the dual problem. So, from the standard form of dual problem, after converting the inequalities into equalities, we get what is known as an augmented or surplus form of the dual minimization problem. And as we are introducing new variables, these surplus variables we do not know their values a priori. So, they would be the decision variables as well. So, the number of decision variables in the model will go up proportionately. So, now we are going to finally discuss the general procedure to solve general M cross N LPP linear programming problem. So, now suppose we deal with M number of constraints which is less than or equal to n, which is basically the number of decision variables. Sometimes they are also called control variables. Okay. So, this is basically the general LP problem. So, now we discuss a special case where m is exactly equal to n. See, there is actually no problem, then the system of equations has only one solution, right. So, we get unique solution. Okay. But now we are going to discuss what if m is less than n, right. Okay. So, to see how in this case where n is greater than m, to solve the linear programming problem, we are going to now introduce two more new concepts which are known as basic solution and basic feasible solution. So, let us first define what is a basic solution to a LPP. Okay. So, basic solution to LPP has at most m non-zero values for the variables. And what is a basic feasible solution? Basic feasible solution is a set of solution values that satisfies all of the constraints and has at most m non-zero values. So, basically for solution of LPP in step 1, you set n minus m decision variables to 0, okay. And then in step 2 solve m equations set n minus m variables to 0, then basically we get m equations in m variables, then of course we can solve this system of equations, and if that is done, then the resulting solution, if it is a unique one, then it becomes a basic solution. So, basically by following these two steps we can get unique basic solution. Okay. So, now let us concentrate on a simplified numerical exercise, and we will try to solve it graphically. So, we are going to work with a numerical exercise now. Okay. And in that numerical exercise, let us simplify the dimension of the problem. So, now we are going to assume that we have two outputs to be produced by the firm, and they are basically denoted by symbols Q1 and Q2. Then these two outputs are produced by 3 inputs, and they are basically given by x1, x2 and x3, right. And now we are also going to assume some values. So, we have to assume the per unit profits if we want to solve a profit maximization problem. So, let us assume that we want to first study the profit maximization problem. So, the firm's problem is to maximize the profit from its production of two outputs, right. So, we have to now introduce per unit profits. Okay. And we know we have introduced two such symbols before. So, P1 let us assume is rupees 2 or $2 whatever, and P2 is rupees or $3 whatever. Okay. And then we have to assume the fixed input capacities, right. So, there we assume, so input capacity, or in other words resource constraints, so they are basically given as these terms B1 for input 1, and that is basically number 4 units of input 1 is available, and then we assume B2 . Okay. So, now we are in a position to state our primal profit maximization problem. So, the firm wishes to maximize profit, which is given by 2 Q1 plus 3 Q2, and it maximizes profit with respect to the decision variables Q1 and Q2 of course. After writing the linear objective function, which is a profit equation, let us now write down the technical constraints and non-negativity constraints. For that, first of all we have to look at the technology matrix. So, now if I write down the technical constraints, I will get 3 of them because there are 3 inputs. This is for input 1, this is for input 2, and this is for input 3, and there will be 2 non-negativity constraints. So, if we now introduce slack variables S1, S2 and S3, then we get the following system of equations. Okay. So, then basically what do we get? We get 3 equations and 2 control or decision variables. Okay. We have to set 2 variables then obtain the solution for remaining 3 variables, right. Okay. And that can be done in the following manner. So, there will be different combinations of variables to get different basic solutions. Let us look at a simple table to describe the procedure. We will not enumerate all possibilities, but I will show you at least couple of them, so that you understand the process. So, now here look at this table. Here I am going to list down the non-basic variables that I choose. So, by non-basic variables I mean the variables which assumes 0 value, right, and the basic variables are basically for those variables which are basically non-zero value, which assumes non-zero values, right. So, here I first assume the simplest possible case where I have q1 and q2 set to 0, right. So, in that case the basic variables become S1, S2 and S3 from this slack form of the LP problem, right. Okay. Then what will be the basic solution from the system of equations? So, of course, we have 3 variables in 3 equations now, because q2 and q1 they take 0 values, right. So, then the basic solution will become 4, 5 and 20. Okay. So, is this a feasible solution? Yes, of course, because this basically gives me the origin point of the solution space. So, here at the origin all technical constraints and non-negativity constraints are satisfied. Now, what will be the value of objective function if I evaluate this solution? Then I get 0, right. Okay. So, the next case that we are going to study is S1 and S3 being the non-basic variables, means that we assume 0 values for these 2 variables, and if we assume so, then basically we have the basic variables as q1, q2 and S2, right. Okay. So, if that is the case, then what is my basic solution? Basic solution would be 0, 4 minus 3. Now, note, is this a feasible solution or not? No, because for the slack variable S2 we obtained a negative number here, which is not permissible, right. So, this solution is not a feasible solution, right. So, as this is not a feasible solution, there is no need to compute the objective function value. So, we will not compute it. Okay. So, this is the way our journey will continue, and we can get a combination of non-basic variables as S1 and S2, and if we choose that, then the basic variables become q1, q2 and S3, and then we find solution 1, 2 and 8. Okay. And is this a feasible solution? Yes, of course, because at this point basically all the constraints are met, right. So, we have yes here, and what is the objective function value? That we can compute to be 8. Now, we can show there are many other possibilities, but we can show that this gives the highest value of my profit. So, this is basically the optimized value or the maximized value of profit expression that I started with. Okay. So, now we are going to prove our point that the last basic feasible solution that we have obtained indeed is the profit maximizing point through a graphical exercise. So, we will continue our discussion on this numerical exercise in the next lecture.